In example 5, we have the equation 2a plus b plus 2c gives me 3x. We have 4 trials of data which we can draw from to figure out the order of reaction with respect to each of the reactants and the overall order of the reaction. Starting with A, I can see that if I double my concentration, my rate actually quadruples. So this tells me that my order with respect to A is equal to 2. For B, when I triple my concentration, my rate stays the same. This tells me that B is equal to 0. For C, I don't have data that is free from changes to the other reactants, A and B here. So I'm going to analyze here, C is doubled, but A is also doubled. That means that my rate needs to equal to my rate being times by 2 and times by 4. Oops. To make sure that I account for all the changes here. So if you do 3.0 times 10 to the negative 4 times by 2 to take this change and times by 4 to take this change, this is what you will get. And that will tell me that my order with respect to C is equal to 1, because when I double C, my rate will double. The rate law for this equation is K times A to the power of 2, B to the power of 0, and C to the power of 1. To find the value of my rate constant, I'm going to work over here. I'm going to work with trial 1. So I have an initial rate of 3.0 times 10 to the negative 4 mole per liter second. K is equal to A, which is 0.1 mole per liter squared, and B, which is 0, so we can omit it. C is equal to 1. Sorry, the overall is 3 when we add those together. So here, C is also 0.1. And it's to the power of 1. When I expand this, I'm going to get 3.0 times 10 to the negative 4 moles liter second, K, and I get overall 0.001 when I do 0.1 to the power of 2 times 0.1. This is the number I get. And I have to remember that my units aren't crossing out here. I have mole squared, liter squared, times mole liter. Now I'm going to divide both sides by my concentration that's given here. Got to make sure you're very careful because it can get a little messy. All right, now I have K is equal to 3.0 times 10 to the negative 4 moles per liter second over 0.001 mole squared liter squared times mole over liter. I can see that I can cancel out this mole per liter. I will be left with 0.30 over 1 over a second times liter squared over mole squared. So since looking at what happened here to flip the liter and the moles, I'm dividing by moles, but I'm also timesing by liter squared since it's on the bottom. So you need to flip those values. And overall, we're going to get 0.30 liters squared second moles squared as our rate law constant for this equation. The next part wants us to calculate the rate of production when A, B, and C concentration is 0.4 moles per liter. We know our rate is equal to 0.30 liters squared per mole squared second times 0.40 mole over liter to the power of 2, because A is a second order and C is the first order. So it's to the power of 1. To expand this, we're going to get 0.30 liters squared moles squared seconds, 0.16 moles squared liters squared, 0.40 moles per liter. Now we're able to cross out our liters squared, our moles squared, and we're left with an answer of 1.9 times 10 to the negative 2 mole per liter seconds. This is our final answer.